In this segment, we're going to look at different types of real-world models. Now, some of these models get a little crazy because you can't really do finite differences. You could plug each and every piece of data into the calculator and try and figure it out. But if you have hundreds of thousands of data points, you don't want to do that. First tip, if you have data that corresponds to a year, then you need to label it differently. Your X values are not going to be the year. You're going to assign your first year as 0 or 1. And then you would count up from there incrementally. So 1, 2, 3, 4, 5, and 6. Now, if the years went by tens, then I would count 10, 20, 30, 40, 50, and so forth. So you need to make sure that you're taking a difference between the years. The temperature is my Y column. So my X would go in the L1 in the calculator. The temperature would go into L2. The X corresponds to the domain, and the temperature corresponds to the range. Now, if you'll notice, there's duplications in the range. Okay? Now, if you look at this data, your first guess, what kind of data do you think it is? Well, that's easy. My first guess would be a quadratic, right? We can do finite differences. We can also look at the R value. But that's my first guess. So we're going to plug that into the calculator. Okay, so here's my data plugged into the calculator. Now I'm going to go into my stat and I'm actually going to calculate. We said it was a quadratic. So we're going to go down to our quadratic. And if I'll notice, the regression is actually R squared is a positive 1. So that tells me that we were right on. Good job. That is a 100% correlation. That means all the data fits this curve. Now let's figure out what the equation is. So I'd have y equals, a is a 1. So I'm going to put x squared. B is minus 5, so minus 5x. And then c is 13. Simple enough. We were actually not asked to predict anything in this particular problem, but if you were to ask to say find y in, or let's say find the temperature, because that's really what we're interested in, right? Find the temperature in the year 2000. Okay? Well, what happens? What is x? What does x equal? Well, 2000 would be what? Let's see, 96 is 6, so 97 would be 7, 98 would be 8, 99 would be 9, so 2000 would be 10. So I would plug in x equals to 10 into my calculator. And it tells me 63. Now, does that make sense? Would my temperature be 63 degrees? That's going to be awfully high for that range, so perhaps it's not really a valid data range. But yes, 63 is a valid number. Okay? Now let's look at a different kind of problem. Here we're estimating the cost for the meal. Estimating the tip based on the cost of the meal. You'll notice none of these values are evenly spaced. So again, we're going to do a linear on this because we haven't been given enough information and you cannot find the difference. My meal cost is my L1, which is my X, which is also my domain. My tip, my output value, would be my L2, which is my Y, or my range. So inputs versus outputs, domain versus range. Let's plug that into the calculator. Okay, so now we have it plugged into the calculator. Let's go to our stat, and let's go over to calc. Now we said we were going to do a linear because we could not do any of the differences because everything was kind of jumping around. The difference from 20 to 8 is not going to help us out much. Okay, so we're going to do a linear regression for this data. And notice your R value, 0.99. That means it's not a perfect fit, but 99% of the data is on this curve. So let's look at what the curve is. Y equals, now we're going to have to round, A is going to be 0.16 x, and then B, that's a negative B, so I should subtract there, 0.299, so I'm going to say that's 0.30. Now they ask us what is the tip if the meal costs $18.50. So we're going to plug that in. We plug it in for x, and we would see that the tip, or the y value, would be equal to $2.66. That's not a very good tip. Maybe this was a few years ago. Okay? And that would be 2 examples of real-world problems. Done.